special evening distinguished lecture by Alexander Barg. Professor Barg is a professor at the University of Maryland. Probably needs no introduction. I'll just give but he's won many awards, and he's a fellow of the IEEE. He's won an IEEE Best Paper Award, and most recently he won the Hamming Medal, again from IEEE. And this distinguished lecture is sort of the celebration of that. So thanks, Sasha, for agreeing to speak, and enjoy.
Thanks very much for the invitation. So, yes. The title clearly overstates the promise. Of course, LP, SDP, for instance, we heard two talks this morning about applications of SDP to decoding. I will not touch on that. And generally, it's a very broad subject across applied mathematics. So this applies to coding. And the first specific problem, I will go beyond that, but it is here on the board. So when this program started, there still is this board with open problems, but the open problem that was there was the GV bound type. It was erased, but from what I understand, the problem has not been resolved yet. And the upper bound is MRRW, McAleese, Rodimich, Ramsey, Welch, 1977, and it still stands as the best bound on codes. So this is difficult. This is simply numbers. They are not associated with any objects, so I'll speak about upper bounds because I don't need to show any codes for that. All right, so this is what this talk is about. Code packings of spaces, metric spaces of all kinds, not all kinds, but several kinds, and we can, of course, call them codes. Optimality, uniqueness, I'll barely mention uniqueness, and this was the general approach. LP was pioneered by Philippe Delsarte. Starting in 1972 and through the 1970s, he basically created algebraic coding theory as we know it. And the impact of his work continues to expand, 50 years down the road. So it's quite an amazing theory that has become only more and more general as time goes by. So this is the outline. This is clear in all the statement. I will not be able to do all of that. So we know MRRW, we have heard of Levenshtein. Kabatiansky-Levenshtein is the same for spherical codes and sphere packings. We will discuss those results. Kissing numbers, sphere packings, that applies, of course, well, for spherical codes, this is for Rn. Sets with forbidden distances, this touches upon constant weight codes, but it is also, of course, a problem, well-known problem recognized in extremal combinatorics, and so forth. Impossibility for LP, yes, we know much less, of course, what cannot be done with LP and SDP, but we do know something. All right, so in the first couple of pages, I will give a proof of this MRRW bound, because first thing we hear it is difficult, then we understand how to prove it, then we invent our own proof. So I did that at some point. So I'll present some proof which I think is easy, but we'll see. So let's start with C is a code in the binary space. I guess I should say the Hamming space. And let's form this sum. We start with summing on vectors of fixed Hamming weight Z, and then we sum on all the code words here, -1 x comma z dot product, and then we do the same thing with y. Well, they are, of course, identical sums, so this is a full complete square, so this left-hand side is non-negative. Let's remember that. So let's join the two inner sums. We get sum on z, x, y, and c, -1 x plus y, z. Right? That's very clear. So let us interchange the order of summation. So sum on x, y goes outside, sum on z inside, -1 x plus y, z. And just little thinking convinces one that this sum depends only on the distance between x and y and not on x and y themselves. So this is what they call a radial function. It depends on the distance. So let us therefore denote it by capital K sub little k, distance xy. And as we said, this is non-negative, so this is still non-negative. This is called Delsarte's inequalities. All right? So that is the first step. The second step, let us look at functions. We want functions, as we said, they are radials. They take values on the Hamming distances. from 0 to real valued functions. Let us define the inner product as shown here. This is basically with respect to the uniform measure on the space. But since they are radial, that they only depend on the Hamming weight, so the uniform measure collapses to the binomial distribution. So this is the standard inner product. And again, it is an easy check that those k's, they are orthogonal with respect to this inner product. So KL is 0. And if so, any function can be expanded into a Fourier, polynomial or series, if you will, where the coefficients are the inner product fki divided by the squared norm. Okay. All right. So Delsarte's LP goes as follows. LP bound, general LP bound. So we think of codes, but we start with a polynomial. Let f of I be a function from the set of distances to the real space. And let us start with the left-hand side. So let's take f of 0. So f is this polynomial, but we need some assumptions for that polynomial. Let us assume that whenever there is a distance in the code, so let's say little I is greater than the minimum distance of the code, then the polynomial is non-positive. And the coefficients, well, they are non-negative, and the coefficient at 0 is positive. So it is a bit strange that we think of codes, but we speak of polynomials, but things come together as follows. Let us write f of 0, times a constant cardinality of the code.
The coefficients are not.
They are these guys.
Got it.
So because
And below the minimum distance, they can take arbitrary.
Yeah. And because of this, we can now, that was f of 0, the code words coincide, but we can add all the code words because we are putting in more and more non-positive values. So this is good. Then we expand f into the basis of those Kravchuk polynomials. And then we say, for one thing, this sum here, as we said, is non-negative. And the coefficients are also non-negative. So we can discard everything, leaving the 0th coefficient. And when the k is 0, this sum is squared cardinality of the code. So then we have this bound. Cardinality of the code is less than the value at 0 divided by the 0th coefficient. Delsarte's LP bound has been established. So now let us use this general recipe to prove MRRW. This proof really requires very few calculations, so let us look at that. Now, let me normalize those k's so that we set this squared L2 norm. I'll write k tilde to indicate that the L2 norm is 1. Why not? That's multiplying by a constant that does not change any signs or anything in my arguments. So this is 1. And then they satisfy this recurrence. Again, an easy check. So let us now look at the space of polynomials of degree up to k. Consider the following operator. So we multiply by n minus 2x, and then the polynomial still stays in the space except for the largest degree. So let us project it back. Let's discard the coefficient at degree k plus 1. So ek is the projection, orthogonal projection, coordinate projection. So we just discard the last coefficient. Okay, that's this operator as k. Let us write the matrix of that operator in the orthonormal basis. The basis of k tildes, the matrix looks like this because of this formula. And this is called, they call this tridiagonal matrix. Well, it is actually, the main diagonal also plays a role, except that it happens to be 0, but it still has to be, it is still thought of as a tridiagonal matrix. Last thing, we need to do a little perturbation of that operator in the right corner. Let me just flash this without discussing this too much, because that's a technicality. So tk is the operator that interests us, and let us take the largest eigenvalue, the Perron eigenvector of that operator. I'm saying eigenvector, it's really the coefficients of the polynomial, or simply a set of numbers, or the program for the Delsarte bound. So I call this the program, or the polynomial. All right, so it's an eigenvector. So once we act on this f by the operator, we know what happens. And those are those little perturbations that I have injected. There is this ak that I'm not defining, but that comes from that tridiagonal matrix. Let's just look at that. And, well, we have an equation for f. We don't know what f is. But we can compute it. That includes the coefficient fk. We don't know fk. So this is still not too helpful for the bound. But remember, there is this fraction, f of 0 divided by the zeroth coefficient. And so there is a hope that the constants cancel. And we maybe don't even need to know fk. All right. So this is the polynomial, the program that we take. The numerator times f itself. Right? So clearly the numerator squares, so this is non-negative. And the only thing that controls the sign is this n minus 2x. If x is large-ish, together with the eigenvalue, then it is negative, otherwise it is positive. So we can control the sign, and the coefficients are non-negative. This is easy. So we compute the zeroth coefficient, the value at 0, and this is the MRRW program. You divide the two, and by the way, once you divide, the fk cancels. This is MRRW bound. That's it. All right. Yes, that's the MRRW bound. Yes? Well, the non-negativity, yes, it is obvious as long as we adjust this x so that it fits the distance of the code. That's completely within our control, right? And the coefficients, they just happen to be non-negative. All right. So this is MRRW. And you see now how this connects. So the maximum eigenvalue of this tridiagonal matrix has to be greater than n minus twice the distance. And so by controlling k, we can control that. And that's the entire bound. And you might say, well, you still don't know the eigenvalue. And we remember that in the classic proof, it was the extremal zero of the Kravchuk polynomial. And for that, we need contour integration, maybe, and that is hard. No, actually, we can go around that. Because Perron-Frobenius immediately places this largest eigenvalue between these two quantities, basically straight from the theorem. And in particular, we know the asymptotics. And now you pretty much recognize the asymptotics over there on the board. That's the bound. So we have proved MRRW in full glory with no calculations. All right. Comments on similar proofs. I will be somewhat brief here, but you will see why I wanted to mention this. Yes, because so we wrote a paper with Dmitry Nogin on that in 2006. And there was a very nice, inspiring paper by Joel Friedman and Jean-Pierre Tillich here. This paper is somewhat similar. It was for linear codes, binary codes, and it also went by spectral graph theory, but very nice combinatorial arguments. And there was a concurrent proof by Navon and Alex Samorodnitsky. And these two papers, they actually worked with adjacency matrix of the ball of the Hamming space, and we worked with this tridiagonal matrix. So the point that I would like to make here is that at some point through in those proofs, one has to say, let this eigenvector be actually a radial function. And once we say that, this matrix actually collapses. The rows get added, the columns get added, and it becomes a tridiagonal matrix. And so we are back in the same rut, and so basically we're discussing the same proof, even though the initial arguments are very nice. Right. So they were, and so we still retrieve the MRRW program, whatever we try. There were other recent proofs by Loeffel-Lineal. Alex, I think, published more than one proof recently, and he really tries to do this with non-radial functions. He has some conjectures and ideas. There is some hope, but this is still unclear if this bears fruit. And it becomes significantly more difficult, by the way. All right, MRRW. So this is the set of references, and those are, the papers that defined a large part of what I know at some point. It's all started with this 1972 paper by Philippe Delsarte, which is cited in all the publications, including, for instance, Marina Vyazovsky's proofs of lattice optimality. So it gets all the way to the Fields medal. And this is his thesis, a work of amazing generality and impact. And it is said that coding theorists are divided into two subsets, those who have read and understood Delsarte's thesis and the others. But jokes aside, this is an amazing work. There is this paper which established beautiful connections with algebraic combinatorics. And this is a survey in '98 that Delsarte and Levenshtein wrote together, and Robert once told me that it was he who put them together. I think that was a fantastic accomplishment. There are books, Brouwer, Core, and Neumeier, distance regular graphs, which are, well, metric association schemes. And there is a recent book by Banai, Ito, and Tanaka. So Banai wrote a first installment of that book in 1986. It was called Algebraic Combinatorics 1, and it took them some 40 years, and they came up with a sequel. A very nice book. All right. So in particular remarks for large distance, today we were discussing codes that are a little away from n/2. So from the theorem that I showed, we can draw bounds for that S, there was that parameter in there. So for instance, we can k minus 1 over k root n. So 2/3 if we take k3, but we can take any k and derive many, many bounds, of course. So it's still from our old work, but there was a recent paper where they derived bounds specifically for this region, for large distance, motivated by low rate communication problems. And well, these results can be somewhat retrieved from those old bounds, but that technique breaks when we want to go below square root n. And at that point, one appreciates the theorem of Michaelis, where he went lit low of cube root n. And he never published that, but luckily that appears in the McWilliams-Sloan book, chapter 17. So that bound is there, very nice. All right. So once we have this machinery, we now can do many other spaces. Curie-Hamming, here you go. This matrix is truly tridiagonal, and you see why for q equal to 2, the main diagonal was 0. And out comes the MRRW bound due to Matti Aaltonen. The expression, the same thing. We can go to constant weight codes, the Johnson space. So now not the entire Hamming space, but codes in the space of vectors with fixed Hamming weight W. So the measure changes somewhat. This uniform distribution becomes somewhat different. It's still the uniform distribution. So we set up the 3-term recurrence, the tridiagonal matrix, Jacobi operator, Perron eigenvector, and we get, this again MRRW bound in the Johnson space. And you will say, we remember that there is MRRW2 bound, which is not shown there in the formula because it doesn't fit on the board, or maybe not on one line in any event. So to get that, we simply take this bound and average over the shifts. This is called the Basel-Leibniz inequality, and that is the MRRW bound. That's where the asymptotics stand at this point. Nothing better is known. But MRRW can be also proved directly from LP without going to the constant weight codes. That's a nice observation due to Eugene Rodimich, not very well known, but useful. It was highlighted in Delsarte's 91 survey, and we used this with Alexei in a paper where we studied binomial moments of the distant distribution of codes. That was kind of a gift to us at that point. All right. For spherical codes, using exactly the same machinery, but with a different set of polynomials, we get the Kabatansky-Levenshtein bound. And this also works for other two-point homogeneous spaces and beyond that. Let me show 2 examples. So symmetric spaces with the corresponding so what happens when we go beyond those nice spaces? For instance, these 2 examples. Those functions, the k functions, Krautchuk polynomials and similar things, they begin to depend on more than one variable. Now, controlling zeros of multivariate polynomials is a difficult task, and generally people don't know how to do that, but eigenvalues are still there. So even though the functions now depend on many variables, we can still write those 3-term recurrences. The coefficients are matrix coefficients. So the matrices are block tridiagonal, but they're still there. We can compute the eigenvalues. So Christine Bashok wrote a very nice paper on Grassmann, bounds for the Grassmann space. And with Munabasu, we took up this ordered Hamming space. So what's that, by the way? Multiplicity codes will be well known in this audience. So the univariate version of multiplicity codes is the Rosenblum-Fassmann codes, basically the Ritz-Solomon codes. And even before Rosenblum and Fassmann published them, Niederreiter considered that metric space for the purpose of numerical integration on the hypercube. And he came up with the same metric. So now this is called the Niederreiter-Rosenblum-Fassmann NRT space, an NRT metric. I will not define it. It's a little bit technical. It's an extension of the Hamming metric of sorts. And, well, you can still compute asymptotic bounds and even non-asymptotic ones. All right. The last remark is, well, there is also Levenshtein bound, which is even more difficult to write, but it exists. And in fact, it is little known, but Levenshtein bound is better than MRRW non-asymptotically. But for all finite parameters, it is better. Asymptotically, it converges to the same place. So let me show how Levenshtein bound, yes, this is already, yeah. How, yeah, take two on the program. And Levenshtein will come out of that. So remember, we need something like this, except that I changed the game. It was also mentioned earlier today. Let's go from 0 to n to minus 1, 1. So let's send d to 1 minus 2d over n. So now 0 becomes 1, n becomes minus 1, and so our distances are between minus 1 to 1, and large distance is closer to minus 1. All right. So this is the Delsarte program rephrased with the non-negative coefficients. So now we need the polynomial to be non-positive anywhere from minus 1 to s. So let us do this from the first principles. This is a functional. Let's optimize it. For that, oh yes, without loss of generality, it's homogeneous. So let's take f of 1, 1. And then seek f in this form. Is this a limitation? Actually, no. Any polynomial that is satisfies this restriction, pretty much any polynomial can be written in this form. So this is still general. So define the functional. The functional now, the numerator is 1. The functional is simply the zeroth coefficient. So we need supremum on polynomials of this functional, which is supremum of the expectation, right? What is the zeroth Fourier coefficient, if not the expectation of the function? All right. How do you optimize a functional? You differentiate. So let's write the Taylor series. This is the first differential, and we need, and where h is a perturbation. It is a function of small norm, 0 at 1, because we cannot touch this condition, otherwise it's arbitrary. All right, so which function cancels this in a product for every h? There's no such function. Except for one. That's the delta function at s. That will cancel everything, but delta functions, they don't really exist. We don't know what that means. They're certainly not square integrable. They're not L2 functions. So, and plus these are polynomials. What is a delta function here? Not clear. So let's simply approximate it, right? On the space of polynomials of a given degree, there is this notion of reproducing kernels. And what comes out is again, once we approximate it, it's the Christoffel-Darboux kernel, for, as they say, for those in the know. And this is the MRRW program. So what they didn't tell us, they optimized the functional. And it took me 20 years to understand that. But yes, so now you see that there is little hope of improving because, or maybe it's the extremum and we are done. Well, no, it's not, because the second differential should be negative definite, but it isn't for the extremum. So it's a stationary point, but not the extreme, but it's the only stationary point. So if there is extreme, it's somewhere on the boundary, but that is difficult. All right. What about Levenshtein? Well, we have subtly ignored this condition that h of 1 is 0. Levenshtein didn't. He said put h in the form 1 minus x times h1. So put it to 0 at 1. All right. Now our functional is of this form, where 1 minus x enters the integral. And so we need to cancel this in a product. But this 1 minus x, it's bothersome. We are not sure what to make of it. It does not allow us to manipulate this formula with the same ease. And so Levenshtein said, change the measure. Put this 1 minus x into the measure, hide it here, and then we're back in the same game with a different measure. So what changes is the set of polynomials. So now our kernel is of this form. I'm not discussing what that means, but this is really the idea. After that, you do the same calculation, and out comes the Levenshtein bound. So this was his contribution. Discovered it in 1977, published in full in 82, and so on. He published a number of. Konelky's bound actually followed the same blueprint for sphere packings, and we shall speak of this in a moment. And we wrote with Dmitry a little paper on exactly this optimization when we're trying to, well, if not improve MRRW, at least to understand it. All right. So that was technical. After that, it's not as technical. So we can somewhat relax. So this is what Levenshtein polynomial looks like. It is non-positive from the distance to -1, and it has those double zeros, and that is not accidental for a number of reasons. One reason is this. If you look at Vyazovska's functions for E8, this is what they look like. She had to force those double zeros, in fact, by multiplying by sine square of something. Her story does not end there by any means. Yeah, there are quasi-modular forms and so forth. So this is much more involved than this proof, but at least there is some overlap. Not the germ of the idea, but a part of the idea is there. All right. This is the function, and this is the Fourier transform of her function. Well, highlights. All of this comes out of Delsarte. As you see, MRRW, Kabatansky, Levenshtein, Kissing arrangements, I will mention those. Optimality, uniqueness, spherical codes, many authors. Kissing number in dimension 4, an interesting argument. Konelky's, energy bounds, universal optimality, the lattices, equiangular lines, distance distribution of codes, and so forth. So it goes on and on. So that all originates with Delsarte's 72 paper. All right, Kissing numbers. Well, how many unit spheres can touch a unit sphere in Rn? In R3, it's 12 or 13, 12 if you believe Newton, 13 if you believe David Gregory. Now we know it's 12. So what is the maximum size of a spherical code in Rn with minimum separation 60 degrees? Why 60 degrees? Well, because unit sphere is unit sphere, so equilateral triangle, 60 degrees. All right. So this is the same question, really, except we are now on the spherical code, not the binary space. So this is Delsarte. LP bounds gives answer in dimension 8 and 24, 1978, but otherwise it does not give the answer. So we might do two things. We can try to modify LP, or we can use SDP. I don't know if I'm getting to SDP, maybe not, but modifying LP works roughly as follows. So that was invented by Oleg Musin in 2003. And I'm showing a polynomial that proves 12, Newton-Gregory problem, in dimension 3. So this is Alexei Glazerian, 21. Takes this polynomial. They are not real numbers. They're exact rational numbers. They don't approximate anything. Well, but it is not non-negative where we need it. We allow some violation. How do we handle that? Well, we allow the angle, if we fix the north pole, the angle that we allow is minus pi over 4. Out there, this is 1 over root 2, minus 1 over root 2. So north pole, think of points that could violate it, that are located somewhere in South America, in Australia. And it is easy to figure out that there can be at most 3 such points without violating the 60-degree conditions. And after that, you convince yourself that they don't increase the value of the polynomial too much. And out comes a proof of 12, Kissing number 12 in dimension 3. So that's LP modified. All right. So this is the icosahedral arrangement, 12 balls touching one ball in the three-dimensional real space. Sphere packings. You will now see with that preparation that Konelky's really is very close. The idea is close. So we need an L1 function, Fourier transform, and then we need a rather fast decline at infinity for the function and for its derivatives for for integrals to converge properly. So let's say it's a Schwartz function. And then we take the function non-positive for all x above 1, the Fourier coefficients non-negative, and that's it. This is the bound on the central density of packing. Central density is the number of centers in a unit volume of the sphere. Why unit volume? Well, because unit spheres, their volume shrinks, right? It goes to 0 and then goes to infinity. So there are many centers per unit volume. And that's central density. And for radial functions, there is this expansion. Now the Bessel functions play the role of Kravchuk polynomials, but otherwise, generally, the idea is the same. So their main accomplishment was really optimizing this function for small dimensions and improving bounds on sphere packings in small dimensions. So that now this is not asymptotics. Asymptotics, it is still the Kabatansky-Levenshtein. It is still not improved. In fact, a variational argument retrieved Levenshtein's bound, but they also optimized it for small dimensions. That was beautiful. Well, from there, yeah, they improved dimensions from 4 through 36, but then there was, this bold exclamation mark when they proved the optimality of E8 and the Leach lattice. Beautiful. We kind of touched upon that, and I will not go into more details. There is even universal optimality. If I get to that, I'll say what that means. So there is a beautiful book by Dan Ramick, recent book, Topics in Complex Analysis, which constructs the Vyazovsky function from the first principles with proofs, and it's very readable. So I highly recommend it. There is Henry Kahn's sort of half-survey paper in the bulletin of the MS in January this year, also on the same story. All right. What about impossibility? What is it that we cannot do with LP? Well, this is what we cannot do. Some good sphere packings cannot be proved by this Kohn-Elkis bound in dimension 6, if I remember correctly, and some small dimensions. We cannot, LP will not get us to the needed result, which is a bit unfortunate, but well, that's where it stands. There is this beautiful result of Alex Samorodnitsky. Whatever you do with Delsarte LP, you cannot go below halfway between MRRW and Gilbert-Warshauer. So something else is needed. And preparing this talk, I was Googling, searching for some nice pictures, and suddenly I stumbled over the blog of Gil Kalai, January 21, and he reminded me of something that I did a long while ago. He said, conjecture asymptotic MRRW is the best that can be derived from Delsarte's linear programming, and what we did in that little paper was we simply computed the LP bound for large lengths. And so the exact optimal falls smack on the MRRW bound. So probably it's not improvable. All right. Few intersections, all right? So this is a bit of extremal combinatorics. A different story. Family of subsets is T intersecting. Family of subsets of a finite set if every pair of subsets overlaps on at least T points. So think finite set, right? In other words, if there's a code of constant weight, family of W subsets, and then the distance is at most n minus t. Well, if the distance is n minus t, they intersect on T points. That is a rephrasing of the same definition. All right. Erdos-Corrado theorem. Again, a major fact. There are books devoted to it. It says that if the distances are from 1 to W minus t, then the largest size is that, and that is attainable. And with a beautiful addition by Richard Wilson, that happens for all lengths, code lengths above this quantity. The original theorem, 1938, was when S was W minus 1. So any pair of subsets simply needed to intersect. And by the way, it's very easy to understand which family is the extremal one. So if they are required to intersect on one point, fix a point and allow everything else to wander around. And that is the answer, n minus 1, W minus 1. That is the EKR extremal family. The quest was to prove that more is not possible, and that is what they did. And the smallest length was a difficult question. There was for small n smaller than that, this is not extremal. This is the final answer. Frankel's conjecture eventually became a beautiful Alswede-Cachatran theorem, a complete intersection theorem, as they called it, where they really uncovered the full picture. The family becomes smaller, different size. Sorry. Of course, it becomes larger. This family is not extremal anymore. There is a nice survey by David Ellis. There is a book, Frankel-Tokushige, and codes with few distances in general originate in Delsarte-Seidel paper of 1977. All right. So I want to show a recent paper that we did on codes with few distances in the Hamming space. So this is Delsarte LP in the constant weight space. It does not matter. We don't need to understand it. It exists. We're already kind of accustomed to this claim. Right? So these are the Delsarte inequalities. So our idea in that paper was, maybe we don't need all of them. Maybe they are not all equally important. Take a couple of inequalities, in fact, maybe 2 or 3, then you can solve them explicitly. Maybe you can prove some nice things, and out comes the following theorem. If the weight is any of these, and the number of distances is any of these, then the largest code with S distances in the Johnson space is given by this formula, and that starts at those lengths. So that's a somewhat pleasing answer. It gives exact answers for the size of largest codes with a few distances. And we have something similar for the Hamming space. With 2 distances, the largest size is 1 plus n choose 2. Again, it's very easy to understand what the code is. The code has the all 0 vector and all the pairs. That is the extremal largest possible binary code with 2 distances. Doesn't matter which. All right. So this is the paper that most likely will be published this year. It's accepted, but the publication queue, I don't know how long that is. All right. So maybe let me skip that. We made some conjecture related to the Sertosh-Corrado theorem, but looking at the time. What shall we do, SDP? SDP is more technical. So what this version of SDP is about, the Delsarte, it speaks about pairs of vectors. So we speak of distance distributions. And very naturally, SDP speaks of triples, quadruples, k-tuples. So we look at the distributions of triple distances. Manipulating this algebraically requires big machinery, and it all started, this is for spherical codes, let me not discuss that. It all started with the work of Poulter-Williger, 1991, when he wrote an extension of Delsarte's theory to matrix algebras of some kind. Schrever published a very nice paper on application of that for the Hamming space. Not application, sorry, backtrack. He actually invented this SDP bound, taking Terwilliger's technique. And then Bashok-Valentin published that for spherical codes, and there is a nice chapter in the handbook of SDP, Bashok, Heisweit, Schrever, Valentin, SDP and its applications, if I remember correctly. All right. Well, this formula is a bit difficult to parse, but SDP bounds, for one thing, there is a consensus that asymptotics cannot be improved with SDP. For that, we would need a growing number of points. So not triples, not quadruples, but many points. But that is difficult to manipulate. What could be improved were bounds on the kissing numbers. Yes, bounds for the kissing numbers were improved up to 23. No exact answers, though. Optimality, recent paper by Condelat-Landhorst, optimality of some spherical codes. And I want to highlight the last 3 entries. So by putting those curved codes on the sphere and analyzing them, these 3 authors proved that they're optimal. And therefore, those binary curved codes are optimal. Let me here highlight another open problem of coding theory. Prove that curved codes are optimal binary codes. This is not known. Now, Levenshtein proved that they're optimal in the space set of codes that with each vector include its complement, so self-complementary codes. They are known to be optimal, otherwise they're not. But based on these results, they made the conjecture that the codes are all optimal using SDP. A beautiful conjecture, and it would be even more exciting if this were true. Equiangular lines. What is equiangular lines? Well, 6 diagonals of the icosahedron intersected the same angle. Every pair of lines intersected the same angle, even though I can't recall what that angle is, but I know that they're all equal. So we are interested in the maximum size of the set of lines through 0 in Rn, such that, yeah, every pair intersects. So that was started by Delsarte-Seidel. And an early result was, if the number of those lines is greater than 2n, and a is the cosine of the angle, then that cosine is an inverse odd integer. Somewhat unexpected, right? But that's what it is. All right. Gerson's bound said that there are at most that many lines. This is the Levenshtein bound. And very recently, a group of 5 authors from MIT proved that for every a for sufficiently large n, this is the maximum number of equiangular lines. That was spectral graph theory. Did not, well, involve and probably could not involve LP or SDP. So there is this answer, but at the same time, if we don't insist on fixing the angle, then Dekan in a beautiful paper, again involving Kerr codes, constructed a family of size n square. So what is the largest number of equiangular lines? Well, it's not an easy question. There were a couple of bounds proved from SDP. So the bound is that if the dimension is less than 3a squared minus 16, that is by Weishan Yu, and they extended it using 4-point SDP bounds. So that's where it stands, and this is from Weishan's paper. Weishan was my student some 10 years back, so we started these calculations. We used SDP to improve the bounds, and I just copied it from his recent paper. And if you look at the online encyclopedia of integer sequences, then this left column appears there under the number 2853, which is a respectably low number, like in that story about jokes in prison, right? Right. Equiangular lines. Maybe let me mention energy, because that was an unexpected application of Delsarte's. So let us have a potential energy. So instead of looking at the error-correcting properties of codes, let us look at the potential energy, where f is some function, a radial function. So this is the energy. So Iudin in 92 proved the following bound. The proof is exactly, well, not exactly, but very close to Delsarte-like proof. So f is our potential. Suppose that h is a test function that is below the potential with non-negative Fourier coefficients, then the energy is at least that. It was not clear for some time why we needed energy. How does it connect to anything else? So here are examples of potentials. Bounds for undetected error. Bounds for the error probability is shaky because it is upper bounds that can be phrased in the form of energy, but then energy gives lower bounds. Having lower bounds for an upper bound is an unclear proposition. Risk potentials, generally in potential theory, logarithmic. Sum of distances. So what is the largest possible sum of distances in a code of a fixed cardinality? So there is a nice book of 2019, full volume on this discrete energy. Not only LP, but generally potential theory. For instance, distance distributions. So many years back, we proved this bound on a distance distribution, effectively using Iudin's bound, which we didn't know at that point, so we kind of re-derived it, but well, now it all connects. So this is what we know, yes, and then having these distance distribution bounds, we did something for error probability of decoding, undetected error, generalized Hamming weights, covering radius bounds for codes decodable into lists of size 2. This is, if you try to draw it, this is what the random codes give you. This is where the distance distribution cannot go for a fixed distance. So we fix the distance of the code, and those are the bounds on the asymptotic bounds on the distance distribution. The only use of this that I'm aware of is indeed, well, there is more than one use, actually. There was a recent work on smoothing where those bounds also proved useful. Energy minimizing codes. Which codes minimize energy? Well, let me again highlight one result that said that E8 and the Leech lattice form, it was known that they form unique minima for this type of potentials, but Kohn and Kumar actually proved that they're optimal for a vast class of different potentials. That's why they name universally optimal codes. And generally, they worked on universally optimal codes. Sum of distances, let me not discuss that. Let me actually, maybe I'll stop here because time is now close to 6 and it's late and everyone is tired. And thanks for your attention.
You mentioned that you cannot improve on LP by using SDP on triples, or for instance, the quadruples. You have to take triples which are growing.
If you want asymptotics.
Because if there are more, otherwise it's impossible.
I don't know. Nobody does. But after many tries, it's sort of a consensus.
If I can ask a question that actually is kind of inspired by a recent paper of Jean-Pierre's, where they defined some sort of quantum decoding problem, and amazingly it turned out that the radius at which you can resolve the problem is exactly the MRRW bound. But so I guess maybe from your perspective, do you think maybe the MRRW bound is not, like it's bounding something other than the distance, like a different parameter of the code, or could you somehow view the Delsarte LP of the relaxation is giving a bound on a different combinatorial property?
Well, I know of the relation of those LP and SDP problems, in particular to Lova's theta. But again, it's so that was in fact Schrever's in part motivation for his SDP bound, because he wrote back in '78 this comparison of Delsarte's and Lova's bound, a beautiful paper where he discussed theta in the context of LP and later SDP. But this doesn't really answer a question. The true answer is I cannot say, I don't know. Those are hard questions.
Yeah, I agree. That's a hard question.
What's your belief? Do you believe the MRRW is tight or
Binary?
binary?
No, most likely the GV is tight.
Sorry.
Most likely the GV is tight. No, MRRW is an artifact. It is this analytic fact that has kind of reached its limits, but there should be things beyond that. But we need a new theory. You see, little tweaks will not take us there, I believe. Some kind of Galois type breakthrough. We need something new from which it will emerge. Maybe small improvements are possible, I don't know, but big improvements, hard to say.
So maybe in that way, in the second MRRW bound basically passes to constant weight codes and gets an improvement. And when passed to other structures beside constant weight codes.
You see, that had been tried. For instance, doubly constant weight codes. Nothing comes out of that. For non-binary, yes, you can improve MRRW2 a little bit, but there have been many improvements for non-binary, in particular because it is not convex for non-binary, at least for larger Q. So it's not that impressive, but yeah, it has been tried and nothing came out of it. Now, you don't have to go to constant weight codes. You can prove it from the first principles. You can massage the polynomial. You can arrange the polynomial as though you went to constant weight codes and retrieved something from there without mentioning them. That is this Rodemich's theorem. That was also used in sphere packings.
If I can ask another question. I've asked this question to other people before, and they told me there's nothing known, but maybe you know something else. But so I'll just try it anyways. Is there any sort of known kind of optimization problem that you can solve if you're interested in list decoding radius? Like some sort of variant of Delsarte's relaxation for this sort of parameter for code?
Well, no.
No?
But
Okay.
we did a bit of cheating. You see, when you have a bound on the distance distribution, you can parlay that into list to decoding.
Mhm.
And with that, we did improve something that had existed before that, but that is really still Delsarte massaged a little bit. So I did mention it, but very briefly. Beyond that,
Is there like some natural bound why it's impossible, or just not right?
no, the question really is there some other combinatorial quantity that would enable us to improve list bounds for using something like this machinery? Not that I know of.
Let us thank Sasha again.